Hello friends, once again welcome in class 12th chemistry by Vijay Kumar Sethi. We were discussing about the P block elements, group 16 elements, and in this video we will discuss about ozone, its preparation, properties and usage, and we will also discuss about allotropic forms of sulfur. First come to the ozone. Ozone is an allotropic form of oxygen. At a height of about 20 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet radiation. As we know, ultraviolet radiations are harmful for the living organism. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone. This conversion will occur only 10%. This product is known as ozonide oxygen. Why this is called ozonide oxygen? Because we will get the mixture of, in the product side, we will get the O2 and O3. That's why this is called ozonide oxygen. Again, you can see this formation, delta H is positive. Means this is an endothermic process. Okay, that's why it is necessary to use a silent electrical discharge and inaudible electrical discharge. That is, we can say actually electrical discharge is spark. So we have to produce less spark. Otherwise, this ozone will decompose to give O2 to prevent its decomposition. An electric discharge is a simply spark, is the release and transmission of electricity in an applied electric field through a medium. By passing the electric current, some of oxygen molecules dissociate and then atomic oxygen combines with oxygen molecules to form ozone. And the mixture thus obtained contains 5 to 10% ozone by volume, and the mixture is called ozonide oxygen. The apparatus used for this purpose is known as ozonizer. If concentration of ozone greater than 10% are required, a battery of ozonizers can be used. Properties of ozone. Pure ozone is a pale blue gas, dark blue liquid, and violet black solid. Clear? Ozone has a characteristic smell and in small concentrations it is harmless. However, if the concentration rises above about 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. What is this nausea? This is an uneasiness of the stomach that often accompanies the urge to vomit. Ozone is thermodynamically unstable. We already discussed this. Why this is thermodynamically unstable with respect to oxygen. Since its decomposition into oxygen results in liberation of heat. That is, delta H is negative. Decomposition of ozone to oxygen is a exothermic process. And at the same time, this occurs with an increase in entropy. That is delta S positive. And these both the factors reinforce each other, resulting in large negative Gibbs energy change. That is delta G is negative for its conversion into oxygen. That's why ozone is thermodynamically unstable. Therefore, high concentrations of ozone can be dangerously explosive. Properties of ozone we were discussing. It acts as a powerful oxidizing agent. Why this is powerful oxidizing agent? Due to the liberation of nascent, it is atomic oxygen when it decomposes. It oxidizes lead sulfide to lead sulfate and iodide ions to iodine. See, this is PbS. This will converting into PbSO4 and O3 will convert into O2. And this I minus iodide ion will convert into I2 iodine. Okay, and this reaction is useful for the estimation of ozone. How? When ozone reacts with an excess of potassium iodide solution buffered with the borate buffer. I think you are familiar with this buffer solution. This maintains the pH. Then iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating O3. That is, O3 is converting into iodine, and then this iodine is titrated against standard solution of sodium thiosulfate. Depletion of ozone layer. Again, you are familiar with this term, depletion. Nitrogen oxides emitted from the exhaust system of supersonic jet aeroplanes might be slowly depleting the concentration of the ozone layer in the upper atmosphere. How? Actually, this NO, nitric oxide, react with the ozone and form NO2 and O2. Another threat to this ozone layer is the use of freons. Freons is chlorofluorocarbons, which are used in aerosol spray and as refrigerants. Now we can see structure of ozone. This is a bent. This is okay. Actually, O3 is the resonance hybrid of these two structures. Okay. Usage. It is used as a germicide, disinfectant, and for sterilizing water. It also used for bleaching oils, ivory, that is hathi dant, floor starch, that is bleaching agent. It is used as a bleaching agent. It acts as an oxidizing agent in the manufacture of potassium permanganate. Now come to sulfur. First we will discuss about allotropic forms of sulfur. Sulfur forms numerous allotropes, of which yellow, that is rhombic or alpha sulfur, and monoclinic and beta sulfur forms are the most important. That is alpha sulfur, which is also the yellow or rhombic sulfur, and another form is monoclinic or beta sulfur. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 Kelvin. First come to the rhombic sulfur, that is alpha sulfur. This allotrope is yellow in color. Melting point is 385.8 Kelvin and specific gravity is 2.06. Rhombic sulfur crystals are formed on evaporating the solution of rolled sulfur in carbon disulfide. Now what is this rolled sulfur? It is sulfur in the form of rods or sticks made by casting molten sulfur. It is insoluble in water but dissolves to some extent in benzene, alcohol and ether, but it is readily soluble in carbon disulfide. Another allotropic form of sulfur is monoclinic. This is also known as beta sulfur. Its melting point is 393 Kelvin, specific gravity is 1.98. It is also soluble in carbon disulfide. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. 2 holes are made in the crust and remaining liquid poured out. On removing the crust, colorless and needle-shaped, okay, this is needle-shaped, crystals of beta sulfur are formed. It is stable above 369 Kelvin and transforms into alpha sulfur below it. So we can see that is alpha sulfur is stable below 369 Kelvin and transforms into beta sulfur above this temperature. And at 369 Kelvin, both the forms are stable and this temperature is called transition temperature. Now you can see the structure of sulfur molecule. Okay, just have a look the structure of this sulfur molecule. Both rhombic and monoclinic sulfur have S8 molecules, and these S8 molecules are pegged to give different crystal structures. The S8 ring in both the form is puckered and has a crown shape like this. This is puckered crown structure. Okay. At elevated temperature, that is about 1000 Kelvin, S2 is dominant species and is paramagnetic like O2. We can say at this above this temperature, S2 behaves like O2, and that's why this is paramagnetic in nature. Clear? You can say this is rhombic sulfur, octahedral shape, monoclinic sulfur. This is needle shaped crystal, and this above 369 Kelvin temperature, this rhombic sulfur will convert into monoclinic sulfur, and below this will convert into rhombic sulfur. Now this the crown structure, that is S8 molecules, are arranged in this like this. This is the arrangement of S8 molecules in rhombic sulfur like this. These crown fit into each other. And in case of monoclinic sulfur, these crowns are arranged like this. This is the difference between structures, arrangement of these S8 molecules. Okay, student? Thank you.